There's a liquid you can buy at any pottery supply store for about $5 that turns ordinary loose sand into solid blocks, harder than concrete. Not cemented sand, not sand mixed with expensive resin. Solid, load-bearing blocks formed from nothing but grains of sand and a clear, syrupy liquid that has been manufactured since the 1800s. You pour it into sand, pack it into a mold, and within hours you're holding a block that can support the weight of a truck. No kiln required, no specialized training, no industrial equipment, just sand, liquid, and your bare hands. The compound is called sodium silicate. Chemists call it water glass. Foundry workers have called it liquid glass for over a century. And the construction industry has known about its binding power since before your grandparents were born. It bonds silica grains together at the molecular level, forming a rigid glass-like matrix that resists compression, repels water, and withstands temperatures that would crack Portland cement into powder. A 16-ounce bottle costs roughly $5 at any ceramic supply shop or online retailer. A single gallon treats enough sand to produce dozens of full-sized building blocks. The raw sand is free in most parts of the world, sitting in deserts, riverbeds, beaches, and quarries, covering roughly a third of the planet's landmass. So why are we still paying $4 per cinder block and $6 per bag of Portland cement mix when the ground beneath our feet and a bottle of clear liquid could replace both? Because the global cement and concrete market generates over $400 billion in annual revenue. And a building material that anyone can make from dirt and a hardware store chemical is not something that industry is eager for you to discover. They did not stop using sodium silicate because the science failed. They stopped promoting it because the economics worked too well for the wrong people, the people being you. This is the story of the liquid that turned sand into stone, and why the biggest building material industry on the planet hopes you never mix your first batch. Let me take you back to where this chemistry was born. In 1648, a German-Dutch alchemist named Johann Rudolf Glauber was experimenting with potash and silica in his workshop. He heated the two together and produced a strange compound he called oleum silicum, or oil of silica. When he exposed the resulting powder to moist air, it slowly dissolved into a thick, viscous liquid with a remarkable property. Anything it touched and dried on became hard as stone. Glauber documented the substance, but had no commercial application for it. His notes sat largely unread for nearly 170 years. Then, in 1818, a German chemist and mineralogist named Johann Nepomuk von Fuchs picked up where Glauber left off. Von Fuchs treated silicic acid with an alkali solution and produced what he formally named water glass, a compound that was fully soluble in water but, once dried, became completely unaffected by atmospheric changes. It resisted rain, humidity, heat, and freeze-thaw cycles. Von Fuchs recognized its potential immediately and spent years advocating for its use as a building material, a fireproofing agent, and a preservative for stone and wood. He published papers. He gave lectures. He demonstrated the compound to architects and engineers across Central Europe. And then the Industrial Revolution chose a different path. In 1824, a bricklayer in Leeds named Joseph Aspdin patented a powder he called Portland cement because the hardened material resembled the prestigious Portland stone quarried on the English coast. Aspdin's cement was made by burning limestone and clay at extreme temperatures in a kiln, then grinding the resulting calcium silicate clinate into a fine powder. When mixed with water and aggregate, it hardened into concrete. Portland cement had one enormous advantage over sodium silicate for the industrialists of the 19th century. It required massive, expensive, centralized manufacturing. You needed a kiln, you needed a quarry, you needed a grinding mill, a distribution network, and a sales force. The barriers to entry were high, and the profit margins were enormous. Sodium silicate required sand and a bottle of liquid. There was nothing to centralize, nothing to monopolize, and almost nothing to mark up. Portland cement became the foundation of modern construction, not because it was the best binder available, but because it was the most profitable one to control. And that single economic decision in the mid-1800s locked the entire construction industry onto a path it still follows today, a path that now generates over $400 billion in annual revenue worldwide and produces roughly 8% of all global carbon dioxide emissions. If the cement industry were a country, it would be the fourth largest emitter of greenhouse gases on Earth, right behind China, the United States, and India. Every ton of Portland cement manufactured releases nearly a ton of carbon dioxide into the atmosphere, roughly half from the chemical reaction of converting limestone and half from the fossil fuels burned to heat the kiln to over 1,400 degrees Celsius. Meanwhile, sodium silicate production requires a fraction of that energy. You heat sand and soda ash together at lower temperatures. The resulting compound dissolves in water and is ready to use. No clinker grinding, no massive rotary kilns burning coal around the clock, no quarry operations blasting limestone out of mountainsides. And here's the part that should genuinely bother you. The science proving that sodium silicate bonds sand into structural material stronger than concrete is not hidden. It is published in peer-reviewed journals. It is documented in engineering databases. It is used every single day in metal foundries around the world. Foundry workers mix sand with 3 to 4% sodium silicate by weight, pack it into a mold, and hit it with a brief blast of carbon dioxide gas. Within seconds, that loose sand transforms into a rigid solid, strong enough to hold the shape of molten steel being poured at over 1,500 degrees Celsius. They have been doing this for over a century. If a sand and sodium silicate mixture can withstand temperatures that would vaporize concrete, it can certainly hold up a garden wall. Researchers at the Crit Journal of Engineering Sciences tested concrete mixes where they replaced standard sand with silica sand and added 1.75% sodium silicate. The compressive strength reached 85.76 megapascals after 28 days of curing. Standard residential concrete typically reaches 20 to 30 megapascals. The sodium silicate enhanced mix was nearly 3 times stronger than what most construction contractors pour for house foundations. The same study recorded a flexural strength increase of over 150%. That is not a marginal improvement. That is a fundamental shift in material performance. A separate body of research on geopolymer concrete, which uses sodium silicate and sodium hydroxide to activate industrial waste materials like fly ash, has produced even more striking results. Geopolymer binders activated with sodium silicate have achieved compressive strengths exceeding 50 megapascals consistently, with some formulations reaching 80 megapascals. For reference, the concrete used in most highway bridges and commercial buildings targets 30 to 40 megapascals. Geopolymer concrete matches or exceeds that benchmark while generating up to 80% less carbon dioxide during production than Portland cement. And yet, if you walk into any hardware store and ask for a bag of geopolymer cement or a jug of sodium silicate binder for making building blocks, the clerk will stare at you like you just asked for a unicorn. The product is not on the shelf. It has never been on the shelf. The entire retail construction supply chain is built around Portland cement because that is where the money flows. Now, let me explain exactly why this chemistry works, because understanding the mechanism is what separates you from everyone who will scroll past this and keep buying bags of Quikrete for the rest of their lives. Sodium silicate has the chemical formula Na2SiO3. It is made of sodium, silicon, and oxygen, 3 of the most abundant elements on the planet. When dissolved in water, it forms a viscous, alkaline solution that penetrates the spaces between granular materials like sand. As the water evaporates, or as the solution reacts with carbon dioxide, the dissolved silicate precipitates out and forms an amorphous silica gel that locks every grain of sand into a rigid 3-dimensional matrix. Think about what happens when you pour wet concrete. The Portland cement reacts with water in a process called hydration, forming calcium silicate hydrate crystals that bind the sand and gravel together. That reaction takes days and requires precise water ratios, proper curing temperatures, and careful handling to prevent cracking. And even when it goes perfectly, the resulting material is porous, vulnerable to freeze-thaw damage, susceptible to salt attack, and prone to spalling in acidic environments. Sodium silicate skips most of those problems. The silica gel it deposits in the pore structure of sand is chemically stable, non-porous at the microscale, and resistant to the kinds of chemical attack that destroy Portland cement over time. The bonded material does not require days of wet curing. Depending on the method, it can reach handling strength in minutes when exposed to carbon dioxide gas, or in hours when air dried in a warm environment. The resulting block is essentially artificial sandstone with a glass-like binder holding every grain in place. In the foundry industry, this process has been refined to perfection. Workers mix clean silica sand with 3 to 5% sodium silicate solution, pack it firmly into a mold, and then pass carbon dioxide gas through the mixture. The CO2 reacts with the sodium silicate, forming sodium carbonate and precipitating silica gel. The sand hardens into a rigid core within 30 to 60 seconds. Not minutes, seconds. This process is called the CO2 silicate process, and it has been standard practice in metal casting since the mid-20th century. Every engine block in your car, every steel valve in your kitchen faucet, every iron manhole cover on your street was likely cast using a sand mold bound with sodium silicate. The metal casting industry trusts this binder with molten iron at 1500 degrees. The construction industry tells you it does not work for a garden retaining wall at room temperature. Let that contradiction sit for a moment. Now here is the part you actually came for. How to do this yourself. Start by sourcing your sodium silicate. It is sold under the name water glass or liquid glass at ceramic supply shops, pottery suppliers, and online retailers. A 16-ounce bottle typically costs between $5 and $8. A full gallon runs $15 to $25 depending on the supplier, and that gallon is enough to bind hundreds of pounds of sand. You want a solution labeled as having a silica to soda ratio of roughly 3.22 and a density of around 40 balmy. This is the standard commercial formulation sold for ceramics and foundry work. And it is the same chemistry used in every published study on silicate bonded sand. Next, get your sand. Clean silica sand is ideal because the grain shape and mineral purity give the strongest bond. You can buy a 50-pound bag of play sand or silica sand at any hardware store for under $5. For the strongest possible blocks, you want a well-graded sand with a mix of grain sizes, so the smaller particles fill the gaps between larger ones, creating a denser pack. Mixing ratio. Combine your sand with 3 to 5% sodium silicate solution by weight. For every 10 pounds of dry sand, add approximately 5 to 8 fluid ounces of liquid sodium silicate. Mix thoroughly by hand or with a trowel until every grain is evenly coated. The sand should feel slightly damp and sticky, but not wet or soupy. If it is dripping liquid, you have added too much. Pack the mixture firmly into a mold. You can use a simple wooden form, a repurposed metal container, or even a plastic storage bin. The tighter you compact the sand, the denser and stronger your block will be. A hand tamper works, a rubber mallet works, a heavy book works. Compact each layer in lifts of about 2 inches for the most uniform density. Now you have 2 options for hardening. The fast method uses carbon dioxide gas. If you have access to a CO2 tank, even a small one used for homebrew carbonation or paintball, you can pass the gas through your packed sand block. Within 60 seconds, the sodium silicate reacts with the CO2, and the block becomes rigid. You can pull it from the mold immediately and it will hold its shape under load. The second method requires no equipment at all. Simply leave the packed block in its mold in a warm, dry location and allow it to air cure. As the water in the sodium silicate solution evaporates, the silicate precipitates and hardens. This takes 24 to 72 hours, depending on temperature and humidity, but the end result is a hard, solid block that you can stack, build with, or use as a structural element. For maximum strength, you can heat treat the blocks. Research published on sand and sodium silicate bricks found that firing them at 800 degrees Celsius in a standard kiln pushed compressive strength up to 12 megapascals, which meets or exceeds the standard for many commercial building bricks. You do not need a professional kiln for this. A homemade rocket stove or even a sustained wood fire pit can reach these temperatures with minimal effort. Ancient potters were firing clay at these temperatures 6,000 years ago with nothing but stacked stones and hardwood fuel. For most practical applications around a homestead, a campsite, or a backyard project, the air-cured or CO2-cured blocks are more than strong enough. Garden walls, raised bed borders, fire pit enclosures, pathway edging, outdoor furniture bases, and small structural supports are all well within the performance range of sodium silicate bonded sand blocks. One critical detail. Sodium silicate bonded sand is not naturally waterproof in the way that fired ceramic is. Prolonged exposure to running water can gradually dissolve the binder over months. But this is easily solved. A coat of boiled linseed oil, a layer of exterior silicone sealer, or even a simple wash of diluted sodium silicate brushed onto the cured surface creates a water-resistant shell that dramatically extends the lifespan of the block. Foundry workers have used sodium silicate molds in wet conditions for decades. The blocks hold up. They just need a surface treatment for long-term outdoor exposure. Exactly the same way concrete blocks need sealing in wet climates to prevent spalling and freeze damage. So why is none of this in your hardware store? Why does no home improvement chain sell sodium silicate block kits? Why does no mainstream survival guide mention that you can make structural building material from sand and a $5 bottle of clear liquid? Because the global cement market is a $400 billion annual machine, and it runs on one fundamental assumption, that you cannot make your own building material. That construction requires industrial products manufactured in centralized plants and distributed through controlled supply chains. A 50-pound bag of Portland cement costs $5 to $7. A 50-pound bag of sand costs $3 to $5. And yet the cement bag is the one generating billions in corporate revenue, because you have been told you need it and nothing else will do. Sodium silicate cannot be patented. It is a naturally occurring reaction between two of the most common minerals on the planet, silica and soda ash. The manufacturing process has been public knowledge since 1818. You cannot build a brand monopoly around a compound that any hobbyist can produce with a kiln, some sand, and a bag of washing soda. You cannot create a contractor certification program around a material that a child can mix in a bucket. And you absolutely cannot sustain a $400 billion industry when the alternative binder costs pennies per pound and the primary aggregate is the most abundant mineral on Earth's surface. The cement industry did not suppress sodium silicate through some dramatic conspiracy. It simply followed the gravity of profit. Products that require industrial infrastructure generate recurring revenue, create dependency, and justify massive capital investment. Products that come from a $5 bottle and a pile of sand generate exactly none of those things. So sodium silicate stayed in the foundry, it stayed in the pottery studio, it stayed in the chemistry classroom, and it never made it to the shelf at the home improvement store next to the bags of Quikrete and the buckets of pre-mixed mortar. Meanwhile, cement production pumps 1.6 billion metric tons of carbon dioxide into the atmosphere every single year. Concrete structures crack, spall, and crumble within decades in harsh climates. Entire countries sitting on billions of tons of desert sand import cement from overseas because nobody told them the sand under their feet could become the building material itself. That last point deserves repeating. There are nations in North Africa, the Middle East, and Central Asia where desert sand stretches to the horizon in every direction. And those same nations spend billions importing Portland cement to build homes, schools, and infrastructure. Desert sand has traditionally been considered useless for standard concrete because the grains are too round and too fine to bond well with Portland cement. But sodium silicate does not care about grain shape. It bonds to silica grains regardless of whether they were tumbled round by wind or broken angular by a crusher. The binding mechanism is chemical, not mechanical. It forms a glass-like gel that locks grains together at their contact points, regardless of geometry. Geopolymer researchers have specifically tested desert sand in sodium silicate activated binders and confirmed that it produces viable construction material. The very sand that the concrete industry rejects as unusable becomes a perfectly functional building block when you change the binder from Portland cement to sodium silicate. That single fact has the potential to transform construction economics across entire continents. And that is precisely why you have never heard about it on a home improvement show. I need to be straightforward about the limitations because this formula is not magic, and pretending otherwise would undermine the real science behind it. Sodium silicate bonded blocks are not a direct replacement for reinforced structural concrete in high-rise buildings or heavy infrastructure. They lack the tensile strength needed for load-bearing applications without reinforcement, just like concrete does. Portland cement concrete also requires steel rebar for tensile strength because concrete alone is brittle. But for low-rise construction, garden structures, rural building projects, homesteading, emergency shelter construction, and off-grid applications, sodium silicate bonded sand is not only viable, it is often superior in terms of cost, speed, and environmental impact. Water resistance is a genuine concern for untreated blocks in perpetually wet climates. Surface sealing solves this, but it is an extra step you should plan for. If your blocks will sit in standing water or constant rain without any protection, the binder will soften over time. Treat the surface, and this problem disappears. The CO2 curing method produces the fastest and strongest results, but it does require a gas source. For someone building in a remote location with no access to compressed CO2, air curing works perfectly well. It just takes patience. A few days of warm, dry air and your blocks are ready to stack. Temperature extremes during curing can affect final strength. Very cold conditions slow the drying process significantly. Very hot direct sunlight can cause surface cracking from too rapid moisture loss. Curing in shade at moderate temperatures gives the most consistent results. The same common sense that applies to curing Portland cement concrete. None of these limitations change the fundamental reality. You can turn sand into a solid building block with a $5 bottle of liquid, a bucket, and a weekend afternoon. The chemistry is peer-reviewed. The process is used industrially every day in every major foundry on Earth. The materials are cheaper and more abundant than anything in the concrete aisle at your hardware store. This knowledge is not new. Johann Nepomuk von Fuchs tried to give it to the construction industry in 1818. The foundry industry adopted it and never looked back. The construction industry looked at the profit margins and walked the other direction. Over 200 years later, we are still buying bags of Portland cement for $6, still pouring slabs that crack within a decade, still pumping billions of tons of carbon dioxide into the sky, and still ignoring a binding agent that turns the most common mineral on Earth into a structural building material for pennies. The sand did not change. The chemistry did not change. The only thing that changed was who controlled the supply chain, and it was never you. If this opened a vault you did not know existed, subscribe and share this with someone who has been throwing money at hardware store concrete when the answer was sitting in the ground the entire time. Every share pushes this knowledge past the algorithm that buries it. Every subscription makes sure the next secret they are hiding reaches you before it disappears again.